All right, let's dive into the hidden world of engineering behind a component you've probably never seen but absolutely rely on every single day. We're going to build, from the ground up, the perfect control valve. So picture the heart of a giant industrial boiler. Inside, you've got water turning into steam under incredible, almost unimaginable pressure. And controlling that water flow? It's not just about being efficient, it's about safety. One tiny mistake here, and things could go very, very wrong. And that brings us to the big puzzle. How do you design something that looks, well, pretty simple, to be both a powerhouse of strength and a pinnacle of precision? It's a masterclass in engineering, and we're going to take this unsung hero apart, piece by piece, to see what makes it tick. Okay, this is our subject, a 4-inch globe valve assembly. Its one and only job is to manage the feed water for a boiler, and it has to do that job perfectly, thousands of times, under some really intense conditions.
So here are the numbers it's fighting against. And that pressure difference? 12 bar. That's huge. To put that in perspective, that's the kind of pressure you'd feel 120 meters, almost 400 feet underwater. Oh, and here's the really crucial part. If the power cuts out, it absolutely has to slam shut, no questions asked, to keep the whole system safe. That's non-negotiable.
So how in the world do you move a valve against that kind of force? Well, you need muscle. A lot of it. So let's start with the first piece of the puzzle, the actuator. This is what provides all the raw power. You know, the actuator is basically in a three-way fight. First, it has to overcome that massive water pressure that's always trying to force the valve open. Second, it's got to fight against the friction from the seals, the very things that stop it from leaking. And third, it needs that little extra bit of oomph at the end to really press the valve into its seat and get that perfect bubble-tight seal.
So when the engineers calculate all those forces, and then of course add a good safety margin, this is the number they land on. The actuator needs to be able to generate, on demand, at least 16,400 newtons of force.
And just to be clear, we're not talking about a simple little mechanism here. We're talking about a compact industrial muscle that can literally lift a small car clean off the ground. That's the strength part of our equation for sure.
But you know, all that muscle is pretty useless if you can't control it. That's where the brains of the operation come in. Meet the positioner. Its job is to tell that incredible muscle exactly what to do.
Now, this is the really cool part. The positioner is like a translator and a massive amplifier all in one. It takes this tiny, faint electrical whisper from a control room and turns it into a perfectly controlled, powerful blast of compressed air. Air that's strong enough to move that car-lifting actuator with pinpoint precision.
And it's got to be fast. The inside of that actuator holds about 2.4 liters of air. The positioner needs to fill or empty that entire space in just a few seconds. That's what we call stroking time. It has to be quick so the valve can react to changes in the system instantly.
But wait, where does all this powerful compressed air come from? Well, any system is only as strong as its power supply. You need a good set of lungs and arteries to deliver that power when it's needed. And this is where a seemingly tiny detail can make or break the whole design. If the tubing, the arteries carrying the air, is too narrow, the actuator literally gets starved for air. It becomes slow, sluggish, and it just can't meet that critical response time. But if you just increase the size to a 3/8-inch tube, boom, the air flows freely, powerfully, and the whole system works exactly as it should. It's a perfect example of how a simple engineering choice can be the difference between success and failure. Okay, so we've got the muscle, the brains, and the power supply all hooked up. The whole thing is assembled. Now for the moment of truth, the final exam. We have to test it to make sure it actually works the way we designed it to. First question, and it's the most basic one. Is it accurate? When the control room tells it to go to, say, 50% open, does it actually go to 50% exactly? This is what's known as a linearity test. From fully closed to fully open and everywhere in between, its actual position can't be off by more than 1%. Think of it like the speedometer in your car. You want it to be dead-on reliable, telling you the truth every time.
All right, so it's accurate, that's great, but the next question is it repeatable? Does it do the exact same thing the exact same way every single time without any slop or hesitation?
And for that, we run a hysteresis test. Basically, where it lands when it's opening to 50% should be almost identical to where it lands when it's closing to 50%. If there's a big gap, it usually means there's too much friction somewhere, and that's a failure. We need this thing to be consistent.
So, after all the math, all the assembly, and all the testing, we can finally step back and look at the report card for a perfectly engineered system.
And here it is. Every single box is checked. From the massive force of the actuator, right down to the specific size of the air tubing, every single part has been carefully chosen, calculated, and confirmed to work together in perfect harmony. Nothing was left to chance.
And that's really the big takeaway here. This isn't just about one valve. This incredible, intricate dance between raw power and intelligent control is happening all around us, right now, in countless systems that quietly keep our world running.
So, the next time you flip on a light, just for a second, maybe think about this little valve. The electricity powering that light didn't just appear. It was almost certainly made possible by thousands of these perfectly engineered components, all performing that beautiful dance between force and precision. It's just amazing to think about the complex world hiding just beneath the surface.